Radio frequency signals are the unseen foundation of modern communication, yet they remain invisible to the naked eye. To demonstrate our practical understanding for the electromagnetic fields and wave assignment, we developed the passive RF electromagnetic radiation monitor. Our objective was to apply the fundamental Maxwell's equations to capture this energy, specifically by converting high-frequency AC signals into a stable DC voltage. By using 1N34A diodes and LM358 amplifier, we successfully turned abstract theory into a real-time alert system that makes the invisible visible. Moving on to the problem statement, we identified three major issues that make this device necessary. First is public health anxiety. With the rapid rise of 5G and mobile technology, there is growing concern in society about how daily exposure to stray radiation might affect our physical and mental health. The second one is privacy and security. As electronics become cheaper and smaller, hidden wireless spy cameras are becoming a genuine threat in private accommodation. People need a way to detect this invisible intrusion. And the last one is, there is a lack of accessible tools. The existing RF detectors are often expensive and complex, making them out of reach for the average person. Since these hazards are invisible, we aim to engineer a low-cost, simple solution that allows anyone to monitor their environment and verify their safety.
Hi, Assalamualaikum. Firstly, have you ever wondered about all the signals around us right now? Your phone or your smartwatch, which you can't even see, but it's there. So our circuit gives us supervision power to catch those signals and react. So it starts with the antenna, which picks up electromagnetic wave using Maxwell-Faraday's law. To process that tiny bit of energy, we are using 1N34A germanium diodes. They are way more sensitive than standard silicon diodes, allowing us to rectify or catch even the weakest RF whispers. Next is the heart of the circuit, the LM358 op-amp. It takes those microvolts and amplifies them into a usable signal. So you notice the 820 ohm resistors. This is our secret weapon. It eliminates any parasitic oscillation within the circuits, allowing us to detect when the high frequency 5 GHz Wi-Fi signals that usually requires much more complex hardware. For the output and power, once the circuit hears a signal, it triggers the LED and buzzer, so you get instant visual and sound alert. The coolest part is super efficient. It barely touches the 9-volt battery until it actually finds a radiation source. It's a simple, portable and effective. That's how we make the invisible world of RF audible and visible. Thanks for listening.
First, we start by soldering the components onto the backboard. It's all about heat control here. Make sure those joints are solid and clean to avoid any cold solder issues or short circuit. Next is the housing. We use a lightweight, custom slotted casing. This part required a bit of patience. You have to tuck the wiring immediately so the 9-volt battery fits without putting pressure on the solder joints. Finally, we close it up and do a quick test. Everything is contained, protected and ready to go. A simple setup but a great way to practice circuit integration. Starting at the DB box and router, the LED immediately triggers, confirming strong signal activity. Even standard wall outlets and tablets emit enough radiation to set off the sensor. High wattage appliances like water heaters show the highest sensitivity. It's a simple, effective way to map invisible energy.
So for the theoretical relation, how does our project relates to the electromagnetic theory? Since our project doesn't involve a coil of wire, it's a tag team effort between a Faraday and Ampere's law. So the first one is the Faraday's law. Usually we think of moving magnets, but an RF wave, which is radio frequency wave, is a moving magnetic field. As it passes our antenna probe, which is our project is a single wire, it induces a tiny EMF or voltage. Since there is no coil to multiply that signal, we use a high impedance like a MOSFET, which is in our case we use op-amp as a substitute. This ensures even the weakest push from the wave is captured instead of being drained away. Next is the Ampere's law. It says that a changing electric field creates a displacement current. Think of it as a virtual current. flowing through the air. This induces a real current in our probe, which is the wire. Because of the high frequency signals like Wi-Fi change so rapidly, they create a stronger displacement current, giving a coilless detectors their incredible high frequency sensitivity.
In conclusion, the system successfully demonstrated the practical application of Maxwell equation as well as wave theory by converting undetectable high-frequency AC impulses into detectable DC voltages through a voltage double circuit configuration utilizing 1N34A germanium diodes. The circuit is capable of detecting electromagnetic radiation from typical interior sources such as Wi-Fi routers, wall outlets, and water heaters. Though the prototype currently struggles with pulsed signals and mains interference, it can be solved by adding a 1 to 10 nanofarad ceramic capacitor after their rectifier, as this will block the low frequency noise from mains wiring. Looking ahead, the system can be upgraded even further with a microcontroller and a display screen. This addition would allow the device to identify the specific type of signal, like Wi-Fi or Bluetooth, rather than just showing that the radiation is present. Thank you for listening.